It turns out, in fact, that what we've just seen is a key general property of orthogonally diagonalizable matrices. Because see, if a matrix is orthogonally diagonalizable, then I can write it like that. Q, orthogonal matrix, times D, diagonal matrix, times Q transpose. Well, let's transpose A and see what happens. The transpose of A is going to be given by the transpose of that product. And we know that transposing a product is done by transposing each of the matrices in the product, but putting them then in reverse order. So we start from the right hand side, we transpose Q transpose. What do we get? We get Q. We place that at the beginning. Then if we transpose D, what do we get? Well, D is diagonal, so the transpose of D is still D. And then when we transpose Q, what do we get? Q transpose, but this time on the right. Wait, that looks familiar. Oh yeah, that's just A. So what that means is that every orthogonally diagonalizable matrix is always symmetric. Okay, that's a nice property. So what we saw earlier was not a fluke, but it was something that is going to happen every time we construct an orthogonally diagonalizable matrix. Well, that's interesting. It's a very nice property, but there is more to it. What? Well, just watch. Now, the previous property, the fact that every orthogonally diagonalizable matrix is symmetric, was actually fairly easy to prove. And, to some extent, yeah, it's nice. And when we look back at the proof, it's not that surprising. What is surprising, however, is that every symmetric matrix is orthogonally diagonalizable. So that relationship goes both ways. In other words, when we're talking about matrices, to say that a matrix is symmetric is the same thing as to say that it's orthogonally diagonalizable. We're seeing here another instance of those situations where in linear algebra, where in fact we're looking at pretty much the same property, but we're looking at it from two different perspectives. So when we say that a matrix is symmetric, we're looking at its entries and the symmetry in the entries between the element aij and the element ajI. When we're looking at the orthogonally diagonalizable matrix, we're looking at how that matrix can be factored as a product of matrices with special properties. But in fact, it turns out that those two things are exactly equal. Every symmetric matrix is orthogonally diagonalizable. Every orthogonally diagonalizable matrix is symmetric. Now, how about the proof? Well, unfortunately, the proof of this second part of the connection is not as easy. In fact, it's fairly technical and very complicated. In fact, your textbook does not even give you the complete proof. It just gives you a little bit more of a sketch of what I'm about to give you. But the technical proof actually is fairly complicated. However, there are two key steps that you want to keep in mind about the proof. The first one is that the proof relies on the fact that any symmetric matrix has only real eigenvalues. Again, it's not an easy fact to see or to prove, but it is true. So every symmetric matrix only has real eigenvalues, so the characteristic polynomial will not have any complex roots, will only have real roots. And the second thing is the fact that the multiplicity of each of these eigenvalues is in fact going to be enough for a diagonalization. These are the two crucial points. Remember that in order to obtain diagonalization, you need enough eigenvectors, and that means that the multiplicities of those eigenvalues have to be sufficient both geometrically and algebraically. So the geometric multiplicity has to be equal to the algebraic multiplicity in order for us to be able to construct it. But it turns out, again, if you start from a symmetric matrix, both of these facts are true, and they allow, together with a whole bunch of other technical steps, to prove that the matrix is in fact orthogonally diagonalizable. Now that we know that, then we can actually do also the construction of the orthogonal diagonalization, pretty much like we did the construction of the diagonalization. Find the eigenvalues, construct the eigenvectors. The only problem is then make sure that the eigenvectors you pick are going to be orthogonal to each other. Now, a little bit of terminology, which will bring us back to our ghost here. Okay? Now, in linear algebra, when we look at the set of all eigenvalues of a matrix, we call this the spectrum of the matrix, okay? And that's where this idea of the ghost comes from. Now, remember, a ghost, it's more probably called a specter, but spectrum is close enough, okay? Also, proving that every symmetric matrix is orthogonally diagonalizable involves finding the set of eigenvalues. Remember, that's one of the steps. You prove that the eigenvalues are all real, and then you have to find those eigenvalues to proceed with the proof and the construction. So because of this fact, the equivalence between symmetric and orthogonally diagonalizable matrices is actually called in the literature the spectral theorem. Okay? So that's where this whole idea of ghosts came from, but it's one that I would like you to remember. The spectral theorem is a very important theorem in linear algebra, and it is one that you may hear later on, or you may simply just boast about the fact that you know what the spectral theorem is, and it does not have anything to do with ghosts.